So, today we will be learning alright about optical coherence tomography. Okay. Right. So, we will start with optical coherence tomography is the today's topic. So, first of all we should know right before we learn about right the technique approach and their applications are enormous. Okay. Before we learn about it, first of all, right, what is tomography? Some of you must be right certainly knowing about it, right. We must have also heard about CT, scan computed tomography, etc. So, basically what it means tomography. So, if we see the conventional, right, just it is as simple as imaging, right, the whatever may be the right maybe a specimen, okay, or a sample, layer by layer imaging of that, okay, is tomography. So, let us say this is a simple this is the box, okay, it is, let us assume it is transparent box, okay, transparent to the optical, right, part within the visible range, okay, for time being, just to understand this, okay, and it has various components in this. So, if we see from the side view, right, from the right side, what we will observe as it is, if we see, we will see overlap of, right, a sphere with a cylinder, hemisphere, cone, there will be some overlap. If I see from front this side also, there will be some overlap of components, but I will not be knowing how these components are placed, right. Of course, from the object which is seen clearly, right, it may be in the front, but the object which is lying in the back will also be seen if the size of the object is bigger than the size of the front object, right, the back side. If it is clearly part of that is seen, okay, the object is also there back side of the front object. However, what at what position, etc., we will not be knowing information about it, right, as it is if we observe. However, if we go layer by layer, so if we take one layer here, one second layer here, third layer here, fourth, and layer by layer we let us say take a section, okay, cut. So, cutting this layer, okay, cutting this layer, okay, removing this, we will see the first layer what it is, then second layer, right, what it is. We can cut one by one layer and we can see what is located where, is not it, right. So, this cutting, this part is nothing but tomography, okay, and tomography right is basically very important and useful to understand characteristics of, right, various tissues, etc. So, it is very much useful in CT scan, of course. This CT scan is also similar to this, but the approach to extract the information is different, okay. The technique to extract the information is different. There also we use X-rays, which is also part of the electromagnetic wave, but which is not visible, it is in the UV range or extreme UV range, ultraviolet range, okay. And when we use X-ray, the difficult situation with X-ray is the X-rays, they are being absorbed by the tissue structures. So, the amount of heat generated will be large enough, the photon energy is very high, okay, h nu, the frequency is very large, wavelength is very short, right, it is electromagnetic wave which is short wavelength. So, h nu is very large. So, photon energy is large, it can ionize the molecules. So, if it is longer, the exposure of X-rays, etc., will damage the tissue also. But if we are using optical approach, the optical frequencies what we are considering in biophotonics are limited to maybe slightly UV range to certain extent up to maybe 355 nanometer or so, and then longer wavelengths we use, visible range 400 nanometer to 700 nanometer, and then infrared range, near infrared etc., maybe up to 2.5 micrometer or so. And this this photon frequencies are not they will not be ionizing the things. Of course, if I use a very high intense beam, there is a possibility, but if you are using within a permissible limit which is quite higher than the X-ray limit, we will be able to access some of the information related to the tissues, specimen samples beneath its surface, and that allows optical technique to be used in a safe manner, and that is why there is some interest in optical tomography. Of course, there are various modalities which can also allow such tomographic sections. So, this picture is the different methods. So, one is of course MRI, magnetic resonance imaging, then ultrasound imaging. It also allows layer by layer information depending upon the acoustic waves which travel and reflect back, the position of that reflection, time of light will help us to determine the layer by layer information. So, that is with ultrasound. Then this is photoacoustic tomography, that also we understood. It is also possible to receive some information beneath the surface of skin surface. Now, optical coherence tomography, here the x axis is penetration depth, that is what is the meaning of penetration depth? The the penetration depth of in this case, in our case, light, electromagnetic wave, So, the penetration depth is comparatively lesser as compared to MRI or ultrasound, PET or even CT scan, it is quite, CT scan can easily penetrate through tissue etc. X-rays can easily penetrate through, while in case of electromagnetic wave, which is optical waves, there is a limit within certain, and the range is, if you go back to our initial discussions on what is the transmission characteristics depending upon wavelengths etc., what we observed that the region around 1 micrometer near infrared region, the penetration depth is significant. If we are working with shorter wavelength, let us say 600 nanometer, 700 nanometer, blood, hemoglobin, melanin, every such molecules will absorb the light. So, the depth of penetration will get limited. If you go towards infrared side, water molecules are they are the ones which have significant absorption. So, basically the depth of penetration is limited to millimeter order or sub millimeter order, Here it is written as 0.1 centimeter, which is millimeter order, or even less. Scattering also comes into picture, very large scattering etc. Thereafter, there are some other methods such as reflectance Raman spectroscopy, fluorescence spectroscopy, or basically microscopy techniques. Microscopy is confocal microscopy, CM, multiphoton microscopy is the recent development. These are all fluorescence spectroscopy, Raman spectroscopy, microscopy techniques such as confocal or multiphoton microscopic techniques are having, they provide less depth of penetration, but they have certain advantages in terms of what we want to observe. Some application areas are there which as are separate, but it is. Now, if you consider OCT, its resolution penetration depth is 100 micrometer millimeter order, and resolution. Now, what it means? What is the meaning of resolution here? The thickness of the layer, that minimum thickness that you can capture terms of information. Okay. So, in the previous part, of course, right, with my hand, see this thickness, how as minimum as possible if you capture, you will get more and more, right, information about whatever is inside. So, this resolution is basically what is mentioned here is axial resolution, right, depth of that direction where the light is propagating and we are seeing the reflected or scattered signal. So, basically this resolution provides axial information, depth information, okay, minimum that thickness. Now, see, in fact this OCT approach, right, was first introduced, the technique which I will describe in the later stage, but the first introduced by James Fujimoto, right, from MIT, Massachusetts Institute of Technology, in 1990s, right, it started, and today most of the ophthalmologists and other some of the applications related to skin, right, related issues, etc., measurements, this OCT technique is very much applicable, okay. And right, so this approach has now become very much universal, okay. As an equipment, it started coming in 2000 or so, year 2000 beginning, as an equipment device which can be used, right, and 2000 now, today it is available in right, most of the eyes specialists, they use this device extensively, okay. So, we will see how they are, how are it's being used. The answer is, right, the depth of penetration, although limited, but it can penetrate to certain extent beneath the skin, great, which is other such devices, X-rays, MRI, etc., cannot give you that much resolution, although it can penetrate, but it will not give you the resolution, it will not give you right, some small changes within that small layer thickness, okay, that can be captured by this OCT. Secondly, it is an optical biopsy, you do not have to remove the tissue and see the information under microscope, you can still send the light, get the information layer by layer, right. Of course, again as depth of penetration may be limited, right, but it is possible. You can couple this approach with endoscopy and you can reach to intestine or gastro, right, intestine information can also be achieved, right, can be attained with this, okay. The principal technique is low coherence interferometry. Okay. Low coherence interferometry means what? So, if you can recall, right, so basically the technique is low coherence interferometry. Now, what is interferometry? All of you must be knowing. And what is Michelson interferometry? Right, you will be able to recollect. In that Michelson interferometer, what are we capturing? What did we capture? Do you remember? Phase information. So, as it is, phase information is difficult to achieve, but with the help of intensity variation, right? Right, and basically it also corresponds to the path length change in the path length, isn't it? That is what we capture, right? Are you, can you recall? Right. So, now what is used as a light source to capture this information? Why do we need laser? Okay, okay, you are telling it should be coherent. Okay, then we can control polarization to certain extent, okay, It is directional, but it is okay. In OCT, it is a small device, it is not long distance dial. So, directionality it is fine. So, right. So, basically it is a monochromatic theoretically, of course, so it is connected with coherence as well, but monochromatic source, right, chromatic source, and spatial as well as axial, right. It is temporal spatial and temporal coherence is achieved. So, we use a laser beam, and if it is a Michelson interferometer, the light propagates through a beam splitter and gets divided into two arms. Okay, same this light gets divided into two arms. So, there is a beam splitter, okay, and then what happens? This is, let us say, a laser beam, and then there is a mirror here M1, and there is, let us say, object or mirror here M2. Then what will happen? The reflected light, okay, from here and reflected light from here, they will reflect, they will reflect partially, get reflected here, partially it will get transmitted also, right. But that is okay, we will not worry about this component, but we will if we see here, right, with the detector placed over here, let us say photo detector, okay, what we will see, if the path length between this position, right, path length L1 and this path length L2, right, path length I am talking about this, right, path length, okay, this path length L1 and L2 are equal, then we will see constructive interference over here, right, because both this light beams are travelling most equal length. So, the path length difference is 0 and the phase, they will be in the phase. So, constructive interference, so indirectly phase information will be represented by the intensity, the signal. So, if this is the path difference, then, and this is the detector intensity, then we will see that at path difference equal to 0, it is maximum intensity you will observe. As this path difference changes, you will see a change in intensity, okay, because at one point where the path difference is such that both these waves, when they meet here, they are out of phase. So, destructive, right, interference, you will end up with a 0 intensity, right, and then again it will increase, decrease, it will keep on, right. And if this light source is monochromatic light source, if it is monochromatic light source, then this interference will keep repeating, okay, for infinite path length. The path length will be very long, okay, sorry, means path difference can be very long, still you will be able to see such interference pattern, okay. So, this is what right we know. So, what basically we know is the path difference is captured over here in terms of the intensity, and path difference is a function of the phase difference, correct. So, 2 pi by lambda n1 L1 minus n2 L2, correct, is the phase, and n1 is the refractive index in arm 1, n2 is the refractive index of arm 2. So, when n1 and n2 are in air, it is equal 1, that is why we did not care here about this path difference. However, basically it is n1 n2 L2 minus n1 L1, which is the path difference, optical path difference, and phase is estimated by 2 pi by lambda into optical path difference, correct. Now, we so indirectly this right, this information is captured in this, and here what we are seeing here using laser, it is a coherence, right, this part, while what we are writing in OCT approach is the low coherence interferometry, okay. So, we intentionally use a light source which is broadband light source, not narrow band, but broadband light source, so that the coherence length, okay. See here, if I am using a monochromatic light source, I will keep observing such interference pattern as this path length changes, and this path length, it can go up to, right, very long distance. Difference between these two path lengths can be delta L, can be very long, still I will be able to see interference pattern. But when we are using a light source which is broadband in nature, there is a limit to this coherence. What we will observe in terms of right, interference pattern. So, if I am using, let us say, a broadband light source, okay, when I say broadband light source, means spectrally broadband, right, spectrally broadband. Okay. That means it has multiple wavelengths associated with it, right. There are different wavelengths, they will all propagate through, and let us say this is a beam splitter as we described in the previous case. Okay. It is going here, this is M2, this is mirror M1, this is mirror M2, and here what we will see, okay, what we will see, the reflected, right, right, we will see some interference over here. Okay, now if the path length L1 and here L2 both are equal, okay, L1 and L2 are equal, what we will see is a very large intensity interference, all the waves, okay, it has multiple wavelengths, right, lambda, not only lambda 1, it is lambda 1, lambda 2, lambda 3, lambda 4, etc. So, it has a broadband, okay, intensity, source intensity is a broadband, correct. It has a certain spectral width delta lambda or frequency width, right. In terms of frequency also it has delta nu, right, delta nu. You know relationship between nu and lambda, right. Nu is equal to C by lambda. So, delta nu is equal to minus C by lambda square delta, is not it, correct. We know, I just took the differentiation, we have already noted. Negative sign, I do not worry much about negative sign because it is a frequency part, right. So, we do not have to worry too much about it, and what we see, okay, 1 minute, somewhere I should coherence, I know what happened, 1 minute, so that oh, okay. Okay, it is okay, it is I'll derive it here, although it is not exactly given, and that is okay. So, now so this is the spectral width. So, indirectly what it represents, okay, the spectral width, it is a broadband source. So, when L1 and L2 are equal, we will see very large, right, intensity difference. So, this is delta L, which is in air, it is L2 minus L1, and in terms of intensity which is captured by the detector, photo detector over here, okay, eye detector will be maximum, okay, when L1 and L2 0, okay, will be maximum. However, as this L2 starts changing, as it starts changing, let us say L1 minus L2, L1 and L2 are not equal now, let us say, and L2 starts increasing or decreasing, in this case let us say increasing. What will happen? The intensity will decrease, okay, and then it increase as it, but it will follow something like this, okay, and then it will reach to a value, okay. Maybe I should, I am sorry, first let me 1 minute, that should be it will go to 50%. Okay, then it will become like this. Okay, so you will not be able to observe, okay, first of all the zero information, okay, you will not, because any point of time whenever L1 and L2 are not equal, certain wavelengths will be having a phase match, right. See, because it consists of so many different wavelengths, so some of these wavelengths will be will be having the same phase with each other, right. So basically, and second point is this starts increasing, L1 minus L2, this starts increasing further after a certain length, you will not see any interference. What you observed in the previous case, right, you observed as you keep on changing L1 minus L2, you are observing this max minimum continuously, but here it is ceased, right, no difference, you keep on increasing the length, there is no information about any phase change. So, the information about phase change is limited to a particular path length difference, okay, and this difference where right, this path length. So, if I drew an envelope, okay, envelope to this, so that gives me approximate this path length difference, to which I can observe this, right, variation in intensity such as like this, okay, variation in intensity to certain extent, and this path length where let us say intensity of the light becomes 1 by E square, okay, of its maximum, 1 by in the sense that let us say this is a center, right, 50%. So, at 1 by E square of this, right, height, when it becomes this length, okay, is known as a coherence length. Okay. So, you will observe intensity variation to the certain extent, which is known as coherence. Beyond that, you will not see any intensity variation, even though the path length is changing. See, in the previous case, as the path length changes, intensity variation you will keep on observing with a laser beam, but in this case, up to certain extent you will see the path length difference in terms of indirectly through intensity variation at the detector end, but then it ceases to change, okay. Intensity will remain constant after this, okay. So, this length, coherence length, this coherence length is of course half of this, right. Actually, mirror image is also here, this, right, you can move the mirror inside also and still you can see, okay, this. Now, this total coherence length, okay, total this coherence length is twice this, right, LC, 2 times LC, okay, in this, is it okay. So, let us say this is small LC and the total coherence length, just to distinguish that, okay, not that, it is big LC, okay, coherence. Is it fine? Now, this how to estimate approximately, right, this coherence length, it is right, it can be estimated, it depends upon the spectral distribution, of this spectral distribution. Okay. So, if the spectral distribution is Gaussian in nature, the coherence length will be different. If it is flat top, okay, flat top distribution, let us say we have a spectral distribution like this, a light source with a spectral width, then it is slightly different, etc. Generally, most of the light sources, if we take a a Gaussian distribution, right, then how do we estimate? So, in general, coherence length based on the Fourier transform, if you take spectral width as delta nu, right, in terms of frequency delta nu, then the coherence time, okay, is given by 1 upon delta nu, okay, it is 1 upon delta nu, right, based on the Fourier transform, okay, delta nu, and coherence length, that is the coherence length, right, speed of light into tau c. So, I am so sorry, this right error. So, delta nu is small, if the laser beam is used, tau c will be very large. So, the coherence length will be large enough, but when delta nu is large, spectral width of the beams, light beam source is large enough, the tau c will be very small. So, tau c represents the phase, basically the time required, very small length within which all the waves have the almost the same phase. Okay. So, as the spectral width increases, automatically the time duration within which all the waves having the same phase will keep decreasing, okay, will keep decreasing, correct, because longer wavelength, let us say longer wavelength, and there is a shorter wavelength, correct, then they have the same phase, that time duration is quite small, okay. So, within which, if all the waves have the same phase, then the interference intensity is going to be the large enough, okay. But as the phase variation comes into picture, the intensity will now be get affected by total sum of all these modes, right, this mode 1, right, mode 1, this is mode 2, all these modes, different wavelengths, right, and a detector over here will only capture the overall intensity, which is the sum of all this interference, right, widths. Mode 1 will interfere with its own wavelength only, okay. So, it will give you certain intensity, then mode 2 will also interfere with its own mode, okay. When wavelengths are different, different wavelengths cannot interfere with each other, okay. Each wavelength, while when the interference is considered, both these waves which are going to interfere should have the same phase and same wavelength, then they will interfere. Of course, there will be some small limit practically, but theoretically it is the same wavelength. So, you can imagine that as the number of modes, wavelengths are increasing, as the spectral width is wide enough, the length within which all of them will add up constructively will start decreasing, and that is nothing but the coherence length, okay. Now, this coherence length is indirectly C by delta nu, correct, C by delta nu, correct, right. So, if I substitute this over here, this of course, it is not equal, it is proportional to C by delta nu, and which is equal to, if I use delta nu as C into delta lambda by lambda square. So, right, LC is lambda square by delta lambda, correct, approximately proportional to, and depending upon the beam shape, spectral shape of this laser, light source, this value LC is given by LC, which is proportional to lambda square by delta lambda, is given by, let us say if it is a Gaussian beam shape, then total, right, coherence length is 4 natural log 2 by pi lambda square by delta lambda. Now, this factor comes into picture because in case of a Gaussian beam, Gaussian spectral distribution, light source, okay, of the light source distribution, okay, it will have a Gaussian spectral distribution. The intensity of each of these beams will be different, right? This spectral, depending upon the spectral, this thing, center wavelength will have different intensity as compared to the other wavelengths. So, all these aspects affects overall, right, this coherence aspect, and this factor incorporates the beams, the spectral shape of the light source and gives us some correction factor, and in case of a Gaussian beam it is 4 natural of 2 divided by pi into, that is the factor, okay, lambda square by delta lambda. If it is a flat top, let us say the input beam is a flat top distribution, this factor may slightly vary depending upon the beam shape, okay, so it will slightly vary. Now, so the right, so this is the total coherence length, and right, coherence length on one side delta lambda is nothing but 2 natural log of 2 divided by pi lambda square by delta lambda, okay. Is it fine? Okay. So, what it means physically, if I start moving the mirror in the previous case, I start moving this mirror M2, this is a light source which is a broadband light source with a spectral width delta lambda or frequency, in terms of frequency, delta nu. If I start moving this mirror M2 slowly, what will I see is the change in the intensity. However, right, it will that difference in terms of intensity change will cease very much within this coherence length, and thereafter the intensity will remain constant, okay, some 50% of that intensity will remain constant. So, so over here delta L, over here intensity, so it will then this, and approximate this, right, where if you see this envelope, then at some point where, right, from here the intensity is 1 by E square, this coherence length is, if the beam source, if this is detector, if the beam light source is a Gaussian beam shape, a spectral with spectral characteristics of the Gaussian of the light source is Gaussian in nature, then this coherence length is 2 log of 2 divided by pi to, right, lambda square by delta lambda. Now, that means whatever information we will obtain, okay, from that particular layer where the mirror, instead of mirror, if I replace it with a tissue, let us say, so I can start from the surface of the tissue till I go to a particular depth, that much information correspond to this coherence length, I can observe the information. Beyond that, whatever may be the tissue characteristics, right, I will not be able to observe at that point, okay. Tomorrow we will see how to observe the depth information further. For that, of course, as simple as you move the reference mirror arm also by M1 changes by small amount, then I will see the other side some little bit more depth information from the tissue. We will see tomorrow how exactly, how are we capturing information. It is hidden in terms of refractive index change. Okay. We will see it tomorrow and go ahead with tomorrow's class and different approaches related to optical, means what are the modalities that we can use to capture this information.